Okay, cool. Just for a quick show of hands, who's here for a discussion at the moment? Okay, nice, cool. We got a nice and small Friday afternoon section. Okay, great. So, see, one of the people on Zoom just raised their hand as well. So today we're going to be talking about a couple of different things. Okay. So we're just going to start off with some discussion logistics. I know we've all had enough of that this week, but we just have a couple quick things to talk about. Then we're mainly going to focus on dynamical systems, which if you guys have checked out the first homework, that's what it's all about. And then if we have a few minutes left over afterwards, we'll talk about a very, very brief introduction to linear control, which you guys might have started in lecture. Okay, cool. So just regarding some logistics for discussion and for content for the class, the way our discussions are going to work is mainly we're going to be reviewing what material is covered in lectures most weeks. Okay. But in some weeks, because we really like to try and cover current research topics in lecture, we're going to give a little bit of an introduction to some more advanced topics that you'll see in the lecture the following week. So you could carry, or so you guys could talk about all the most recent stuff. Okay. So regarding your homework assignments, they're going to work a little bit differently to 106A, if you guys have looked at homework one. So generally our format for the homework is we're going to provide you guys with a little bit of theory, like background on the question, before the actual question itself, just so you know what you're doing when you get started, okay? And I'm also going to be releasing a set of notes for each homework around the time that each homework is released as well, all right? So the first set of that has been published as of yesterday, I believe. And yeah, do let me know if you have any questions on those. If you notice anything that looks weird, it's probably wrong. So just let me know if you see any typos, anything like that, or if there's something that you think isn't covered in there that you'd like us to cover, then yeah, do let us know, and we'll really try and put something together for that. Okay. So by the way, if you're over there and I can't see you over the shelf, just give me a shout, and then yeah, it's kind of hard to thread in the way. Yes. So. So it won't always be that way, but just for some certain lectures, it will be. So for example, next week we'll be introducing the Lyapunov stability in a discussion section, and then the following week in lecture, you'll be talking about some research applications of that. At the moment, that's the only one that we have planned to work that way. For the most part, you will be introduced to all your new concepts in lecture. But yeah, just in some rare cases, we'll talk about some new stuff in the section first. Yeah. Okay, great. Do we have any other logistical questions before we get started? How are we doing? Wonderful. All right. So we're going to start off by introducing a couple of different concepts in dynamical systems. All right. And then we'll get a little bit of practice working with the types of problems that tend to come. Okay. So please just do stop me anytime. Give me a shout, raise your hand, anything that works for you if you have any questions. Okay. Wonderful. So to start out by talking about dynamical systems. Okay. So what actually is a dynamical system? You know, it's a very fancy sounding name, right? It's got a kind of cool mathematical name, but really all that it is the system whose state changes in time, right? Like if you have an apple that's like falling from a tree, or some computer that's sending information over a network, all of those things are dynamical systems, right? They're all pretty different, but they really all just fall under some belt. As long as we have something that's changing, something that's moving as time passes, it's going to be a dynamical system, okay? So in 106A, right, we really talked about these systems that we could describe with Lagrangian dynamics, right? So Lagrangian dynamics. And we derived different equations of motion for all these different systems, right? So we saw something like, mx double dot equals some input force, like Fn minus mg, okay? Just to make something up, right? And just to clarify it, when I write these two little dots above, what I mean is that we're taking the second time derivative of this, right? So double dots equals second time derivative. All right. So we just use this dot notation to try and keep things nice and tidy, right? If we're taking like the nth derivative, we won't have to write all these different things all the time. We can just save ourselves a little bit. Okay. So what we're trying to do in this class, right, is we're trying to go from this starting point where we had these Lagrangian dynamics equations that we used to work with different possibilities. We're trying to go from that point and really generalize our discussion, all right? So how do we generalize our descriptions of systems is our main question today, okay? How do we generalize All right. So, in general, our differential equations can look a lot more wild than just the simple like f equals ma kind of form. Right? We could come up with something totally crazy, right? I'm just gonna come up with something that's really purposefully obtuse over here. So we could have maybe like x double dot cubed equals sine of x triple dot squared plus cosine of x, right? And even though that thing looks totally nuts, right? That's a valid differential equation, right? That's something that maybe there is actually a solution to. Okay. So something that we notice between these two things, right, is that there's a lot of stuff that's going on here. Right? These differential equations that we described, they can have all sorts of forms out there, right? And this is something that's going to be kind of problematic. So ODEs have all sorts of forms. Okay, so they can look something like this, or maybe they'll look a little bit simpler, something like that. We could really come up with anything under the sun, and that's going to be a valid ordinary differential solve. So if we're trying to really generalize our discussion here, it's going to kind of be a problem, right? Because if we're trying to describe, how we come up with some controller for a very general nonlinear system that can have any sort of dynamics, right? If we can have something that looks like this and something that looks like this at the same time, those two things look totally different, okay? But we still want to describe them with the same general framework. So how are we actually going to do that? So our main concept here is that to develop a general theory for describing systems, what we need is some sort of convention, all right? So we need some conventional way to write a differential equation. A differential equation. All right? This is going to be really important for us in this class because if we come up with this nice general framework for writing differential equations, right? We can maybe design feedback controllers for all these general equations all at once, right? We won't have to take each thing case by case. Maybe we could say, hey, we know what the general form of a differential equation is. Maybe we could just go straight to coming up with our feedback controller and just have a single general formula for everything, right? If we could do that, that would be super, super powerful. So we have this great idea that we want to generalize this theory of describing differential equations. Okay. So do we have any questions so far on our sort of motivation over here? Why we're looking for this general form? Need it? Yeah. What are we thinking? So? Yeah. Oh, that's describing systems. Yeah. Yeah. Sorry about that. So describing. Yeah. If you can't read anything I've written, please do let me know. Okay. Great. How are we doing over there? Feeling good? Okay. Cool. Okay, so let's get started on representing this framework. All right, so if you guys have started your homework on question 1, you might have seen this already, but otherwise we'll just, we'll go over how we sort of set these things. Okay, so our general framework for these easy nonlinear systems is going to be something called the state space representation. All right, so we have this really, really powerful idea in nonlinear systems, nonlinear dynamical systems, that we can describe any sort of system out there, no matter what it is, in the following format. All right. So we can describe any system using the format of two equations. All right. So I'm just going to write out what these equations are, and then we'll go back and talk about the different points that go into them. Okay. So for right now, I'm just going to write them out. So we're going to have x dot equals f of x on the u, and we're going to have a second equation, y equals h of x. All right. So if x is going to be an n-dimensional vector, right? So I'm going to write x is in Rn. U might be an m-dimensional vector. We have different number of variables in U that we have in x. So I'm going to write Rm. And finally, y could also be a different size vector, right? We're just going to keep things very, very general. So y, I'll say, is a p-dimensional vector. Y is an Rp. Okay, So let's talk about the different components of this definition over here, right? What do these variables x, y, and u actually represent? What are these functions f and h, and how does it actually relate back to our idea of generalization? Okay, so let's talk about some different components of the state space model. So different components. All right. Well, first up, let's think about what that variable x is, right? X is usually a pretty important variable in algebra and stuff like that. If we named it something important in this case. Okay. So x is something called the state vector of the system, all right? So state vector, that vector x in Rn, okay? So it's this guy that shows up over here, all right? And what the state vector does is it contains the minimum number of variables we need to completely describe our configuration of the system in one time. Okay? So it contains all of these variables we need to completely describe our system. With our system configuration. All right, so if we had something super simple like a mass that's maybe moving around on the spring, we could totally describe what that mass is doing just by using its, say, position and velocity. All right, we'll formalize that a little bit later, but in that case, all we need is maybe the position of the mass, its velocity. All we would put in our state vector is just x and x stuff. Okay. So when you're thinking about a state vector, what you should really be thinking about are positions in your system and velocities in your system. Okay. So we'll talk about why just those two are what we need in an example a little bit. Okay. So if our state vector has, all these things we need to completely describe the current state of our system, right? What are these other variables actually for? So another thing that we have is this vector u. Okay. So that brings us to our next vector in the system. So we have an input vector, which is this u in Rn. Okay. So that was that one that we highlighted in blue. Okay. So what's really important about the state vector is that although it contains all these things that completely describe the state of our system, we don't have direct control over those variables. Okay? So we don't have direct control. So the variables in the system that we do have direct control over, all right, that we ourselves can say apply to the system or move in the system to change something, total control over its value. Okay? Those are what we put in the input. Okay? So an input vector contains all variables we can directly control. All right. So if we had the example, say, a car that I'm driving, right? Maybe our state vector would contain the position of the car, orientation of the car, the velocity, things like that. But those aren't things that we can directly control, right? What we can directly control in the car is our angle of the steering wheel. And we can move the steering wheel ourselves to be anywhere that we want. And so we might put the steering wheel angle in our input. Okay. All right. So our inputs we can entirely control, and we can use those inputs to change the behavior of our system. Okay? All right. So we have one remaining term that we're going to talk about over here, and that is this term y. Right? So y is what's known as the output vector. All right? So that's that y in RP. Okay. So we're not going to talk so much about this second equation in this class. This is more something that you would see if you took a class in feedback control. You tend to work with this output a lot. But what this output essentially is it's a vector of all these variables that we actually care about in our system. Okay? So it contains variables of interest. What do I actually mean by this in a more practical sense? So let's say we're driving our car around, but we only actually really care about the position of our car. If we want to move it to a certain location, we're not really interested in maybe in the velocity or the orientation of the vehicle, right? We just want to go ahead and stick it at a particular position in space. Right? So our output in that case would just maybe be the x and y position of the car, right? Because those are the only things that we actually care about, right? So our output is going to be a function of our state vector, and in some rare cases, the input vector as well. And it's really just going to extract all the information that we ourselves care about when we're moving the system. Okay. So I really want to emphasize these outputs. They could be any function out there in the system. Right? We can entirely control what they are. And they have nothing to do with the actual, physical laws governing systems. Okay? So we entirely decide. Okay. Now, because of these different names of these different vectors, right, we can actually give two names to these equations up here. All right. So since this first equation, right, this one, is describing how our state vector is changing, we call this the state equation. All right. And the second vector is describing the output. We call it the output equation. All right. Great. So together, the state equation and the output equation, they form this model called the state space model of the system. All right. So this forms state space. Okay. So I know that was a lot of content right over there, but do we have any questions about this jump? Yes. Yeah. So, yeah, that's actually an interesting point. I would imagine that it would come from like the space of possible states of the system. Say we're moving around in Rn. Yeah, that would probably, probably, if anything, be what it is. Yeah, so usually, if you're describing something in control, a lot of the times in different theorems, they'll say, pick a vector x from your state space. So I think it might just come from the convention that these vectors actually belong to some sort of space. Yeah, yeah, that's a good question. Yeah, do we have any other questions? Yeah. Is there a vector that just efficient the state vector times or yeah. So y is also going to be a function of t. So you can imagine it like we solve this differential equation up at the top. We figure out what x of t is, and then we plug that in to get our output. Yeah, yeah, that's a great point. So it's not always going to be the position. It's really going to be just whatever we care about. In a lot of cases, it will be the position. So in some cases, in state estimation scenarios, there'll actually be a vector of things that we can measure. So it can vary here and there, but yeah. Yeah. What's up? Yeah. So our dots denote derivatives. Okay. So dots equals derivative. Okay. So if I write x dot, that just means dx dt. If I write x double dot, that would be d squared x dt squared. And it just saves us the trouble of having to write out that. Yeah, so in general, all of our equations are going to be with respect to time. So if you see a dot, just automatically assume it's with respect to time. Yeah. If it's with respect to anything else, we'll generally just write out the full like dy dx or something. Yeah, yeah, that's a great point. Okay. Great. So if we're feeling good about this, we can start to talk about some sort of problems that come up with this, right? If we take a really close look at our governing equation up here, right? The state space that's meant to represent absolutely everything else. Right? What do we notice? Well, we only have a first derivative right over here. That's the first derivative. But if we think about the system that we were describing with Lagrangian dynamics, right? We had this mx double dot equals some forces, right? That was a second order equation. If we come up with all these arbitrary differential equations, right? They can be nth order. You have the nth derivative of the function. So how are we going to take these nth order functions, right, and write them in this first order format? Right? Is that going to be a problem for us? Is that something that we can actually do? Well, let's see. Okay. So our main problem now is that we have an nth order equation, but want to write it in state space, which is first order. Okay. So what do we do? Okay. So solution to this problem, I'll keep it brief and then we'll jump into an example for that, right? Is going to come in the form of something called phase variables, all right? So we're going to use something called phase variables to solve this problem. All right. So let's outline what we have. Okay. I'm just going to start off with a simple scalar case. Okay. So we have the nth derivative of x e to the n. Right. So when you take the nth derivative of a function, you can usually abbreviate it with these little parentheses and then an n up there, right? Just because we can't really write like n dots over a function. So we have the nth derivative of x is equal to some function f of x. All right. We're just going to keep things nice and easy for now. Let's say x is a scalar, right? X is a norm. Okay. So what we want to do is we want to somehow rewrite this function in state space, right? Take this nth order differential equation and somehow write it as a first order equation with an equivalent behavior. All right. So what are we going to do? Well, what we could do is we could define sort of this magic change of variables. All right. So we have magic change of variables. Okay. So here's what I'm going to do. I'm going to define some new variables, right? Q0, Q1, all the way up until Qn minus 1. Okay? What are these variables going to be defined as? So I'm going to define Q0 just to be equal to x, right? Simple scalar basic variable. Okay? Q1, I'm going to take that to be the first derivative of x. All right? Q2, I'll take to be the second derivative of x. We can keep going and going and going, keep taking derivatives all the way up until we get to our lost variable, Qn minus 1. Right? And that is going to be the n minus first derivative of x. Okay. So we have all these different variables. Right? What I'm going to do now is I'm going to go ahead and package them all together into a vector. Right? So we're just taking all these variables, we're just putting them one on top of the other. Q0, Q1, all the way to Qn. Right? So these variables are great, right? But we actually have to put them to use somehow, right? So we know that eventually, right, we're looking to get some sort of first order differential equation out of this. So maybe we could try taking the derivative of q. We could see what sort of things that gives us. All right. So I'm just going to clarify right over here. This is an n-dimensional vector, right? Since we have Q0, Q1 all the way until Qn. Okay. So let's try taking the derivative of q. All right. Take derivative of q. What's that going to look like? So if we do q dot, right, we're going to have to take the derivative of each of these little variables. Okay, so let's start out by taking q0 dot. So if I do q0 dot, let's finish that bracket over there, that's going to be equal to x dot, just by definition of it, right? But if we look at our next line over here, what's x dot equal to? X dot's equal to q1. Okay, well, that's kind of interesting, right? So q dot, we'll put in q1 as our first thing. Okay. Now what about q1 dot, right? Well, that's going to be the first derivative of x dot. Okay, so that's going to be x double dot. But when we look at our definitions over here, x double dot is just q2. All right? We keep going and going and going all the way up until we get to qn minus 1 dot. All right? So remember that qn minus 1 was defined to be the n minus first derivative of x. So if we take another derivative, what do we end up with? We end up with the nth derivative of the function. All right? But if we look all the way at our defining characteristic for the nth derivative, we said that was equal to our governing equation for our differential equation, right? So that thing is just equal to f of x u, or just rewriting it in terms of these q variables, f of q0, comma u. Okay? So if we write out our entire vector of derivatives, let me just rewrite this for a little bit more clarity. Q1 dot, qn minus 1 dot. We write them out using these things over here. Q0 dot we found to be Q1, Q1 dot we found to be Q2, right? And that pattern continues all the way until we got this f of Q0 coming in. All right. So what we see in this lost line is that we preserve the behavior for our original differential equation, right? We still have that f of Qu showing up. It's the same exact equation as our original one. But using these different phase variables, right? Q1, Q2, Q3, all these different variables, we managed to rewrite this nth order system as a system of n first order differential equations. Okay? So we took nth order system, changed it to a system of n first order differential equations. All right. So that's what the idea of these phase variables allows us to do. Okay. So we see that doing this, we were able to successfully write our system in state space, right? We had this original nth order system. We were able to rewrite it as a first order one. Okay. So how do we feel about this topic? What do we think? Yeah.
This is question in nodes that shows X and stage.
Oh yeah. So I just used slightly different.
Okay, so that's
yeah, it's the same as yeah. Yeah. What's up? Yeah. So yeah, that's a good question as well. I think in this case, the phase variable might come up from the fact that if you deal with certain second order differential equations that are used in describing vibrations, different orders of that will give you different sinusoidal functions that are out of phase with each other. So I think it might just be extending that idea that we need to break up these higher order derivatives to figure out these different signal functions. So that would be my best guess for that. Yeah. Yeah, great question. Do we have any other questions about this? Yeah, great. Yeah. So that really is what we're doing. It's just that we're now keeping track of all these other different variables that help us, take this thing from just one big equation that we're tackling all at once to all these little equations. So you can think of it like we're going from here, we're integrating it back one step, integrating it back one step, all the way until we get up to yeah. Yeah, that's very good. Yeah. Okay, cool. All right, so let's try a practice problem for this. Right? So this is going to be problem one from the discussion worksheet that's online, but I'm just going to rewrite it up here. Right? So problem one is on Quadrotor dynamics. Okay, so the dynamic equations of a quadrotor, a simple planar quadrotor, strength to move in the xy plane, or excuse me, the yz plane, can be described as follows, right? So negative f times sine of theta and z double dot is equal to f cosine theta minus fg. And finally, we have an I times theta double dot. Okay, so I just want to stress all of these are scalars here. Okay, great. So our question in this problem is, can you convert this system into state space form? All right, so convert these three equations into state space form. All right, I'm going to give you guys a hint to get started on this one. Okay. This is a little bit different to the problems that we've looked at before. Right? Now we're actually already starting with these three different equations that are all coupled to each other. So how do we deal with that? So our short hint for this is going to be find phase variables for each equation and combine all of those different phase variables for each equation, one big vector, all right? And combine all your phase variables into one vector. Okay, great. So do you guys understand what we're trying to do over here? What this question is asking? Is there anything? Yeah. So our inputs are going to be F and M. So it's a force and a moment. For now, don't worry too much about describing this force and describing this moment. Yeah, really just focus on trying to put it into what that is. Okay, so I'll give you guys 3 minutes to do that. If you just want to turn and talk to the person next to you, 2 people. Section. Yeah, let's see how we're going to get on with this problem.
Yeah.
All right, let's just take one more minute and finish things up, right? Then we'll come back together and solve it. Okay, so I hope you guys had enough time to just maybe get started on the problem, maybe not finish it, but maybe even got some thoughts about where to start. Okay, so let's start out with one question. What is our state vector x, or what are our phase variables? Our phase variables. Okay, all right. So does anyone have any ideas what phase variables we might choose? Yeah, yeah. So those are three of them, right? So we have an x, a y, and a theta. But these are second order equations, right? So do we need any derivatives of x, y, or can we just not? So we're trying to break this up into the first order equations. So maybe we don't need the second derivatives. Maybe we can just get away with the first derivative. Okay. So we'll see what that is in a sec. Um, so we can maybe choose an x dot, a y dot, and a theta dot. All right. Okay. So do we have any questions about how we arrived at these variables? How we solve it? Yeah. Oh, I'm so sorry. Yeah. Yeah, so that should be a Z and a Y over there. Yeah, good catch. Y, Z, Y dot, Z dot. Okay, yeah, perfect. Wonderful. Okay, so what happens, right, when we get to the second order part of this equation, right? Why can we just get away with using first derivative over here? Okay, so I'm just going to put this together in a vector. I'll call it Q, right? So remember, our goal is to only have to take the first derivative of this vector, right? So if we do Q dot, what do we get? Well, we get a Y dot, Z dot, theta dot, Y double dot, Z double dot, and theta double dot. Okay? So we see that when we take the first derivative of this vector, that's what we get the second derivative shown. For that reason, we don't need to include them in the original state vectors. That first derivative, get all the second derivatives. Does that make sense? So we could then go ahead and solve for each one of these, right? I'll just do one just as a quick example for the sake of time. So if we solve for like y double dot, for example, looking at this equation, it would be like negative f over m sine of theta, right? And we can see that this thing is only depending on all of our known variables, not taking it. other random derivatives. So we could do the same, solve for your z double dot, solve for your theta double dot, right from your thing. Okay. So just as a general rule of thumb, the highest derivative in your state vector, is one lower than the order of your original differential equation. Okay, and that's just because ultimately what we're doing is limited up to one below. If the first derivative, we're right in that order. Okay, so in this case, right, we had all of these second order differential equations. So in our state vector, we included everything up to the first derivative, right? One below the order. Okay, so do we have any questions about this problem? Okay, cool. Please do stop me anytime, even if you want to jump back to this problem. Okay. All right. Wonderful. Let's talk a little bit about some linear differential equations. Right? So linear ordinary differential equations. Right? So even though we're talking about so y dot, z dot, theta dot are where really just going to get define, right? So if we were to just like write it out directly over here, it would look a little weird, right? It's just like writing y dot is y dot, z dot equals z dot, and then theta dot equals theta dot. But that would really come from the fact, right, how we like define these state variables up here. So you could think of like q1 and your y dot in setting that. So yeah. So here I've sort of kept it in terms of this, but if we call this Q0, Q1, Q2, Q3, Q4, Q5, we could actually rewrite this thing as here, dot, Q1 dot, Q2 dot, Q3 dot, Q5 dot. And then over here, we have y dot is equal to Q3. Z dot is equal to Q4. And theta dot is Q5. And then when we take y double dot, it's negative f over m times sine of theta was our Q2 over here. Sine of Q2. So it really comes down to writing it in terms of these definitions that we made. Does that make sense? Yep. So generally we won't really be huge sticklers for it here. We'll really just try and tell you super clearly if we want you to write it in terms of Q or not. Really, it'll be fine. Yeah. They're just referring to the same. Yeah. Yeah, great point. Okay. We have any other questions? Okay, cool. So let's talk about linear differential equations of the form x dot equals a times x. Okay. So we're going to take x to be a vector in Rn, an n-dimensional vector. And this means that we're going to take a constant matrix in R n by n, right? It's an arbitrary n by n matrix, real values. Okay. So if we have some initial condition, right, x at n0 is equal to x naught, the solution to this differential equation is going to be x of t e to the a times time times x0. Okay. So if you guys remember from what you just say, or maybe from the class that you took, this thing over here is called the matrix exponential. Matrix exponential. All right. And it's simply defined just according to the Taylor series of e to the at. Okay. So e to the at is going to be the identity matrix plus at plus at squared over 2 factorial, and so on. Okay. And things are really just going to keep on going. Okay. So our main question here regarding this matrix exponential, right, is that it's an infinite series, but we want to use it, we want to apply it to solve these practical differential equation problems, right? So are there any particular scenarios where we can actually calculate what the value of that infinite series is directly? Okay? Are there any special forms of A that allow us to do this? So this leads us to our second example problem, all right? Problem 2, where we're really looking for an exact form for what this matrix exponential converges to. Okay, so what I'm going to say is, suppose this n by n matrix is diagonal, right? Diagonal. And n is going to look something like the following, right? So we're going to call it lambda 1, lambda 2, all the way up until lambda, right? Since it's a diagonal matrix, everywhere else is 0. Okay, I'm just going to write those big zeros for us. Okay. So what I want you guys to try now is to show that e to the at for the simple diagonal matrix over here is calculated with the following formula. Right? E to the at is lambda 1t, e to the lambda 2t, e to the lambda nt. Right? And there's some zeros everywhere else. Okay? So we're trying to show that this crazy looking infinite series definition using all of these big matrices for the simple case where A is diagonal converges to something that's relatively easy to write out. Okay? So I'll give you guys another 3 minutes if you want to try and tackle this one. And just try and get started on the problem. See if there are any thoughts or any main avenues of thinking that might lead you to the solution. Okay? So I'll give you guys 3 minutes. If you're feeling it like you don't really know where to start, just give me a shout and I'll come over and give it to you. Okay? Thanks. I just want to try and talk to the person next to you again. That would be great. All right. So let's try and regroup and see if we can solve this problem together. All right. So what is the solution to this problem? Okay. So does anyone have any like good ideas? Good signs? What do we yeah. So where would we start with that? Like, what's our first step in like working with this side? Mhm. Yeah. Okay. So that's a good idea, but we're really going to try and work with this one more from scratch. So if we're working with the idea that we're taking the derivatives of both sides, that's not necessarily meaning that those two sides are Because when you take the derivative of something, even if those derivatives are equal, they could be off by a constant. Okay, so that little plus. Okay, so yeah, that's a great idea. But do we have any other thoughts about this? Yeah, yeah, sure. Let's write out the exponential. All right. So e to the at in this case, right? Let's use this diagonal form. So the first thing is just the identity matrix, right? One's all down the diagonal, zero is everywhere else, right? Then we have at, the lambda 1t, lambda 2t, so on and so forth, all the way until lambda nt. And then we have our squared term, which is 1 over 2 factorial. And the square of a diagonal matrix, right, is just going to be the same thing as squaring each little element along the diagonal. Okay? So this means what we're going to get is we're going to get a lambda 1t squared over there. Okay? Lambda 2t squared all the way until lambda nt squared, right? Zero is everywhere else. And this pattern is going to continue on, right? We add together each little term in there. We get 1 plus lambda 1t plus 1 over 2 factorial lambda 1t squared. And that's going to keep going. We're going to get like 1 plus lambda nt plus 1 over 2 factorial times lambda nt squared plus so on. Okay? Now, do we recognize each little term in there? Right. So each element in there is going to be the Taylor series for the exponential of e to the lambda 1t or e to the lambda nt. Okay? So that gives us e to the lambda 1t, lambda 2t, lambda nt. Okay? All right. Wonderful. That concludes our proof. Do you have any questions about so we can talk very quickly about our final sort of topic for today, which is going to be a super, super brief introduction to concepts relevant to stability and control. All right. So let's talk very briefly about stability. Okay. And we're going to be pretty mathematically informal today. And next week, we're really going to come back and be much more rigorous about this concept of what it means for something to be stable. Okay. So I'm going to start off by making a definition. So we say that xe, pair of a state vector and an input vector, is an equilibrium point of x dot f of x if 0 is what we get when we plug in this point to the dynamics of our system. Okay? So what we're saying is that a point xeu, a particular combination of a state vector and an input vector, is said to be an equilibrium point of the system if when we plug it in, our state vector isn't changing, right? X dot is equal to 0 means our state is completely frozen. Okay? So our system is frozen when we're at an equilibrium point. All right. So how can we evaluate if an equilibrium point is stable or not? So in very basic words, we say if we start near to an equilibrium point, and after we start near there, we manage to stay near there afterwards, and stay near after, the point is stable. Okay. What we're saying is if we have some point for which our state vector is frozen, and starting right near that point means that we're going to stay right near that point, then that's going to be stable. Okay. So a little sort of demonstration of what this actually looks like in a physical. This is going to be a little pendulum today. Okay. So we have two equilibrium points. Our lower one down here, state vector is not moving. If I start near this point, I'm going to move it a little bit away, swing it, and stay very close to it. to us, but maybe it's a little new mathematics, right? If we take the other point on this end, move away from the depth, and we start it a little bit away, this whole thing is just going to swing right down. So that point's unstable. Even though we started right near it, right? We didn't manage to stay near. The pendulum's not going to put itself back up. It's just going to swing right back. Okay? So if you want to think about stability in a sort of intuitive sense, right? What it means for something to physically stable, just remember this idea of start near, stay near. Right? Start near that point, we stay near, pretty much going to stay. Okay? That should be just about it for discussion today. Next week, we'll pick up where we left off with stability, and we'll talk about how we made this. Enjoy the homework and the projects. And yeah, just shoot us a message on Ed or anything else if you have any questions.